We left off topic 3.1, looking at this idea of wanting to take the derivative of both sides of an equation where maybe we had functions of x's and y's floating around. And we said that we were going to be able to do that, to differentiate both sides of that equation with respect to x through a process that we call implicit differentiation. And it might be worth, before we dive into what implicit differentiation is, let's kind of cover what explicit differentiation is, because that's actually what we've been doing for the last unit or so of calculus. So explicit differentiation, which would be the opposite of what we're going to be doing here, which would be implicit differentiation. But explicit differentiation refers to the process of taking the derivatives of functions of x, meaning everything has kind of began with f of x or g of x equals. Our functions have been functions of x. And we've been taking those derivatives with respect to the independent variable, with respect to x. So for example, if we said that we had the function y equals 2x cubed, and the reason this is called explicit differentiation is because we have y defined explicitly as a function of x. Then we could say that, and I'm going to use Leibniz notation here because it actually comes up in a lot of what we're going to be doing today. So rather than saying y prime equals 6x squared, we also said that we had this notation where we could say the derivative of y with respect to x was 6x squared. And that's the process that we've hopefully become very good at by the time that we're at this particular lesson in calculus. So that's what explicit differentiation was. You were given a function of x, you took its derivative with respect to x, and you spent a long time learning some of the various rules. Here we applied the power rule along with a constant multiple to take the derivative of y with respect to x. The process of implicit differentiation, that is going to occur whenever we want to take the derivatives of functions maybe not expressed in terms of x, where we have maybe one side of an equation that has functions of y and functions of x. So implicit differentiation is going to allow us to take the derivative. In particular, it's when our derivative rules prompt us to take the derivative of functions of y. And we'll still be able to do that with respect to the independent variable, with respect to the variable x. And it's a really neat process, and it's a really important tool because we do get to take some of these curves that maybe we could graph where things are expressed in terms of x's and y's. For example, later on in the next video, we'll look at the equation of a circle, and we'll actually be able to describe the rate of change at any point on a circle. And we can look at all sorts of other functions expressed in terms of x's and y's that'll allow us to do that. So we're going to be able to do this process, and it really relies on us being able to use the chain rule in order to do that. Now then, what the chain rule stated, just to kind of simplify some of the language we had in the previous lesson, the chain rule states that if I want to take the derivative where we said y was a function of u, and we later used the u to represent the function of x, but here if I wanted to take the derivative of y with respect to u, so this is a function of u, then what we did was we took the derivative of y with respect to u. So we differentiated the function in terms of how it was presented. We differentiated the outer function with respect to u. So here in a moment, when we want to differentiate a function of y, we will differentiate it in terms of y. And then we will multiply it, the chain rule said, to multiply it by the derivative of u with respect to x. This is how we outline the chain rule. And you can kind of see if we replace u and we would obviously not have y equals here. But if I wanted to take the derivative with respect to x of a function of y instead of u, well, we would differentiate the function with respect to y times the derivative of y with respect to x. And so what we would do here, let's kind of state this again now in terms of functions of y. To take the derivative with respect to x of a function of y, what the chain rule says we do is we will take the derivative with respect to y times the derivative of y with respect to x, which we already have notation for. This idea of the derivative of y with respect to x, that we'll multiply it, we already have notation for. That's what we refer to as dy over dx. So just as a very quick example here, and we'll kind of build this into the context of more complex problems. But for example, let's say I wanted to differentiate with respect to x the function 3y to the fourth. What this idea of implicit differentiation is telling us is that we take the derivative of 3y to the fourth, a function of y. We're going to take its derivative with respect to the variable x. What I do first is I take the derivative of 3y to the fourth with respect to y. I'm going to apply my general derivative rules, which is going to say that is 12y cubed. But because I'm differentiating with respect to x, this chain rule part right here says I need to multiply by this dy over dx. So the derivative of 3y to the fourth with respect to x is equal to 12y cubed times dy over dx. And something really interesting happens in some of these problems we're going to be working. We're going to actually take the derivative with respect to x of both sides of an equation. And from time to time, if I'm taking the derivative of a function of y, I'm going to get this dy dx. And then algebraically, we're going to be able to solve for dy dx, and we're actually going to be able to get a statement that says the derivative of y with respect to x equals some statement very similar to how we got dy dx equals right here. It's a little bit more complicated because we're not given functions explicitly stated in terms of x, but this idea of implicit differentiation is going to allow us to find dy dx the same way we did here, but with functions that are expressed in terms of x and y.